started, so it's the final afternoon. We all had a nice lunch break. So we're back with Saleem to continue the exploration of the 21 centimeter line.
Yeah, thank you, Rebecca. Okay, thanks for coming back. This is the last kind of half day and the last invited, kind of big lecture. So you are exhausted completely, especially after lunch and wine and all of that stuff and swimming. So I'll try to go easy on you, although this part of the talk is a bit the more complicated. But but I'm not gonna, I'm not. So my purpose here is to give you a broad brush of where we stand. What are the issues with observations? Why this topic hasn't produced something yet? What are the complications? Despite 20 years of work on it. What did you say? Ah, okay. That's fine. I thought you were already clapping, so that's why I stopped. Yeah. You were impressed with a few words, that's it. I covered everything. Anyway, so after that, I'll tell you where the observations are. Where we, and the progress. There's a lot of progress in this field. Hopefully, we get more, and there's lots of promising future. And I'll tell you a few issues about how you, also with the data analysis challenges. This is a kind of a very challenging problem, and the theme will be how challenging is this. Right, in the whole, so it's not. I hope it's not too depressing, but it's just that's the main thing. Okay, so yesterday I showed you this figure, and I showed you this equation below. Obviously this is an average figure where we have basically we average over these terms as a function of redshift, and this is what you see here. So we have two purposes in this field. One is to see the average, if we can, and the other to see the fluctuations. And it turns out that there's one technique which is very simple that can tell us about the average, observational technique, but it's very problematic. The other one is interferometric, which tells us about the differences, therefore explores the fluctuations, which is not less problematic. So that's the so let me go back just to explain what I want to do here. First of all, I want to tell you about techniques how to get the average behavior of this delta TB, the brightness temperature, differential brightness temperature, as a function of redshift. So this is in principle a very simple measurement. I want to look at the whole sky or a large chunk of the sky, get what's the brightest temperature of that chunk of the sky, it's the average over whatever I see, and I record it as a function of frequency. That's it, redshift, right? And there I go. So in principle, to do that, you just need one antenna, one thing that looks at the sky and averages over most of it, right? And that's what people started doing some time ago. Actually, I should have... and I'll start with the edges experiment, which probably everyone heard about the edges experiment? Yeah. So, but I should have started again with history. These were not the first guys who looked at the sky in this way. The first is a group of astronomers. One of them is Ravi Subramanian from India. The other is Ron Eakers, and they proposed a kind of a Christmas tree type of antenna, which has many kind of wavelengths. So it goes, so each is kind of a pyramid, not a pyramid, a cone. And each part of the cone is sensitive to a different frequency because of the wavelength. And you get it as, and then you measure what you measure from the sky. This is the same, and they did kind of tried that, and it was very complicated because the antenna wasn't that perfect. The edges guys, led by Judd Bauman, produced a very carefully designed antenna. So in principle, this is cheap as well. It's just this antenna. That's the whole observatory. It's something like this, right? These tend to measure wavelengths, if you remember, 21 centimeter at rest frame, at redshift 10, about 2 meters. So this is about 2 meters type of sensitivity, and normally you don't do the 2 meters, you do a quarter of that or something, because that's enough to get the signal. So it's something like this. It's not big. It's very well shielded, well designed, etc. And in 2018, they dropped the bomb. I mean, I used to ask my late colleague, Gerdy Brown, who will feature in a number of slides here, what do you think about this? He said, no, we'll never get anything from this. But that was his. But in 2018, they dropped an absolute bomb, which, if true, it will change the phase of physics. It would have changed the phase of physics if it's true. And I remember when the results, which I'll explain in a little bit more detail, in 2018, it was published in Nature. So Nature contacted me to comment on this, kind of send me the paper before. So I said, if it's true, it's great. But then, 1, 2, 3, 4, 5, 6 kind of things that might go wrong. And what the quote they put from me, it will change the phase of physics. That's the only quote they put. So even Nature is sensationalist. So be aware when you talk to journalists, even scientific journalists. Anyways, so what did they do? This is their measurement. They have this thing. It looks at the sky. It doesn't see differences in the sky. It just looks at the whole signal that comes from the sky. You can design. You can calculate the beam, what we call the beam, how much it sees. Basically, it's like the kind of the PSF, if you will, of this telescope, and it's half the sky. It's really a big thing. And then what they measure is the temperature, the brightest temperature, as a function of frequency. And these are the frequencies that they measure. So you look at this, you say, there's nothing there. It's just very smooth. And this is what we expect the synchrotron radiation to be. So I'll go to maybe I should have started a bit different, but this is how I started, so I'll explain a little bit, go ahead a little bit and tell you that there are 4 grounds for these experiments, for these measurements. And one of the most dominant foregrounds is the synchrotron. And synchrotron is very smooth, right? That is one of its properties. Namely, it's featureless almost. And this is what you see. This is mostly from our galaxy. This is synchrotron of our galaxy. And you can see the signal in terms of temperature. It's of the order of 5,000 Kelvin. Remember yesterday, I told you the signal that we are looking for, the fluctuations, are of the order 28 millikelvin. It's this equation, tens of millikelvin. Am I? Yeah, this is the number, millikelvin. Whereas what we measure here, thousands of kelvins. So that's 1,000,000 times more than our signal. That's a lot. So they fitted a line here. So you fit a polynomial and take out whatever is left. And they left out with this, which is a bit. So they saw that they have this feature here. So they refitted again with another step with this type of function. And so it's a polynomial plus this. This is the leftover. And they claim this is noise. Therefore, we have a signal that we measured that's not smooth. It has this structure between 90 and 60 megahertz. 60 megahertz, to remind you, is about redshift 12, 14, something like that. And this is even more, 17, and this is ends at redshift 12 or something like this. And it's a whopping signal. If you remember, this is minus, if you look at the coordinates here, at the axis here, it's minus half Kelvin, 500 millikelvin. This is really, really, really large. And it has this very strange structure, etc. It has this bottom here, etc. And how do you explain something like this? Again, if you remember, I told you gas is cold, and it pulls the brightest temperature down before it gets heated. But in most of our models, we got a kind of minus 0.1, minus 0.15 Kelvin, not minus half Kelvin. Yes, please. That's the signal with the noise. Oh, this is what they fitted after the noise. Basically, they said, okay, I mean, you have to do it in a couple of steps. So once they found this, they also wanted to smooth it more and get something out of it, because the initial smooth, polynomial was not smooth enough, or didn't have enough freedom. So they had to do it again. You do it in 2 steps, like many of these things, and you end up with this plus this gives you this, right? That's what you end up with, and you know the noise. So you have a signal of this type, right? And it's warping, minus 500 millikelvin, minus half Kelvin. That was in no, kind of, there's nothing that gives us this. So people started thinking, what can this be? Many people, kind of criticize the way they fit. Some people, theoreticians especially, if you are a theoretician physicist, like how, I'm now in the border, but how, like my education, you explain everything. There's no problem. You've come up with models that explain it. That's the mark of a good physicist. You can explain it. So what's the problem here? So let me go back. I'll tell you a little bit about the physics. Where this negative stuff comes from. At these redshifts, there is no ionization. So this term is almost 1. Yeah, in most of the case, in most of the kind of space. This 1 plus delta. Delta is tiny, right? That's the cosmological fluctuations at redshift 15. That's very small. So what drives the signal is this. Okay? And because it's negative, it means the CMB is larger than the spin temperature. And you can estimate how, so you know what the CMB is, 2.7 multiplied by 1 plus the redshift. That's the temperature of the CMB. I mean, we know it. So that gives you a spin temperature, which is coupled to the gas. So the gas has to be very cold, much colder than would we expect from just passive evolution, like I showed you yesterday. What is colder than gas? Dark matter. Cold dark matter, that's the paradigm, right? But cold dark matter doesn't interact except gravitationally. That's the whole idea, is that cold dark matter interacts with normal matter mostly gravitationally, or with weak interactions, like the neutrinos, right? The neutrinos come from weak interactions. So people start inventing models. So it's cold, but not completely cold. It has some kind of coupling to the gas. So they invented a whole class of a new class of cold dark matter, dark photons, things like, and I remember that year when this was, I went maybe to 5 conferences of particle physicists. They loved it. And they invited, people who know about this. And my role in these conferences to say, wait a minute, which became boring after a while. I don't know why they invited me, because I was the skeptic. It's not to say that this is wrong, but it's to say that just, these experiments, you need to understand exactly what you're doing. So that's one option. Another option is, there's another option, is to change the CMB. What is the CMB? It's photons that have certain frequencies. So maybe the universe produces more of these. So you can have this to be very small, but you can have this to be very big. Then this is not the temperature of the CMB. It's the temperature of photons with the frequency of the CMB. And you can have radio galaxies, things that are produced by the galaxies themselves. So these people played with many models. So this is from the physical side. All of them were a bit awkward, I must say. Very awkward. Most of the models that first people came up with the CDM, with kind of interacting dark matter, turned out to be ruled out by the CMB itself. Planck has all kinds of limits on all kinds of models. So the first paper that was published immediately after this was published in, oh no, not this one. Immediately after this one, in the same issue of Nature, this appeared in Nature. Just a page after that, there was a paper by Barkana, and who tried to interpret it with this CDM. Turned out that the model he proposed was ruled out already by the CMB constraint. So Anyways, and this has kind of excited the field, because this is the first measurement we have. This is very exciting if it's correct. But again, I mean, the problem is that you have so many things that can go wrong. And there are many, many, many papers that were written. And none of them, some of them criticized the fitting, some of them criticized the understanding the noise, because here, so I'll tell you what is the issue here with the fitting. You have a polynomial. Which degree of polynomial you put here? you can put, degree 4, 5, 6, 10. Then this will be absorbed completely by the polynomial, more or less. So people have started arguing these types of things. So you need to know how many degrees of freedom you have in your foregrounds a priori to fit the proper thing. So there was lots of issues. These are data analysis, important data analysis issues. However, the most convincing explanation was in a paper that looked at it and said, there's something wrong with the site. So and I must say, before I go to that, the group that did it, the Bauman group, were very careful. They looked at every systematic that they can look at in their data. So they are really very good group. So I'm not saying anything bad about them. They were very careful, tried everything they could think of. At the end, they said, okay, this is what we have. Let's publish it and see what people say. And eventually, one of the papers looked at this and said, look, there are vegetations here. It means there are vegetations. There are plants. And there is water, right? Plants means water. So there might be in the response of the ground, there might be some structure, right? And that was the most convincing, actually, because that was real. This is something that's very hard to think of a priori and very hard to model as well. So you have to. As a result, another group, Sarah's group, who was doing this. I told you this started from Indian and from the Indian side. And Singh is a student of Subramanian, Ravi Subramanian. So he knew the issues. And they started with Saras 1 and Saras 2. That's the name of the experiment. The third one, they decided, OK, let's put it in a lake, very quiet lake and very deep lake, where I know the response. There's no structure in the response. I know exactly how it responds. And lo and behold, this is what they find after they fit. Very little. So where do we stand now? Saras rules out edges with a 2 sigma, right? So, which is not very significant, but it's serious. Which points that maybe what edges have found is this. Basically, is the issue of the ground, what we call ground plane reflection. Right? That's the issue, or response. Is this the last word? No, because edges are still insisting that. I mean, they are, again, very good. They try all kinds of things. They still claim that their signal stands out because they have also measured it at different frequencies. They have a replica of the same antenna, but with twice the size, which means that you can replicate systematics, you can replicate all kinds of things. And they claim that they didn't see it. For me, this is convincing. Whether this is the last word or not, again, I mean, I always say, you cannot know what nature will do a priori. Never bet against nature. So this might have been correct. This might have been how nature really behaves. Therefore, when I criticize this, that's my view at least, I'd say we have to wait until this is kind of more firm. I never said this is rubbish. You shouldn't say that. And as an evidence, we see these black holes without stars nowadays. I mean, that's amazing. It's just incredible. Yes, please. Yeah. It doesn't matter so much in this case. You have to prepare. I mean, there's a lot of work on preparing the ground here. You don't see it. There's a mesh here underneath it, and they build all kinds of planes. So in order not to have a good response, a good stable thing. The other thing I want to mention about these experiments, which is true for all of them, just a second, this is put outside in the desert. This is in the Kuru Desert. It is in the Kuru Desert or it's Arizona. I can't remember. I think it's in the Kuru Desert in South Africa. I can't remember anymore. This is really pioneering stuff in the sense that you go to nature and do crazy things with it and rely on it to behave nicely to your instrument. There are rodents you have to worry about in some of these experiments. There are all kinds of stories. They are very nice stories. I might tell you some of them if I have time. Yes, please.
Why does the Saras experiment not pick up any signal?
Because it picked up signal. This is the signal. But once they fit, there's nothing left over. So most of all the signal is this is the basically with their sensitivity is the synchrotron radiation from our galaxy. There is nothing above that. They don't see it. So it also, this behavior that you have something here and here flat is mostly instrumental stuff. I mean, or something that is not nature. Nature doesn't behave like this. So that's why one of the criticisms that people have, I had that. This is a strange behavior for a line like this. You would expect an absorption line or something like this. Why there is a floor like that? You know, there's lots of issues. So that's the story of the simple experiments. There should be, these experiments are done because, first of all, one has to explore them. They are very cheap. They are not, I mean, the other experiments, which I will start talking about, the interferometers, cost hundreds of millions of euros. It's not, there's not a cheap business. Whereas this, with €1 million, you get a very nice antenna that looks at the universe. And it became a fashion. So many people try to kind of produce their own antennas and look at the universe. So far, this is the situation. Maybe it will change. Again, don't bet against the universe. Nature always surprises us. But when you deal with something like this, you have to be incredibly, extraordinary claims require extraordinary evidence. And it's one temperature at one frequency as a function of... Yeah, there are other things that are more into the philosophy of science, and I'll mention it because it's important to think about this when you are a theoretician. When you propose a model that solves a problem, like the ones that are proposed by some of the people, like this very kind of cold dark matter that is coupled to the gas a little bit, you should ensure that there are evidence other than the case that you are trying to solve. Right? This is Popper's kind of, Karl Popper's. If you have a theory, it needs to have ramifications, other things, predictions that you can test. And this one has very limited predictions. It predicted this, which is kind of fitting, but nothing else. It will disappear. In galaxies, it will not show up. In other, so it's problematic on the even philosophical point of view. Okay, so let's go. So now the next thing is the other branch of this is the interferometers. And as you see now, there's lots of them. And the first one to start is this 21 CMA, that's in China. They actually brought off-the-shelf antennas. If you are young, if you are old like me, you remember the rooftops of houses in cities. They all had these very long antennas that were used to watch TV, right? It's the same technology. The technology is very simple. Of course, so it's this one. It didn't produce much. And as far as I know, it's not active anymore. The other attempt was also one of the early attempts using GMRT, which has been kind of refurbished, and which is the giant meter radio telescope, the giant meter wave radio telescope. That's in India. It's a marvelous piece of astronomical. That's why India is a powerhouse in radio astronomy, because this has started very early. And they tried to measure. They had some upper limits, but they were very weak, etc. They published it. There's a paper called Pachiga et al. And you will see it later. So it's not active. Then there was this, Then the first one started, after that was LOFAR, which is us. So this is in the Netherlands. You see this, what they call in the Dutch superturp. That's the super mound, which is a circular area, the very center of LOFAR. I'll expand on LOFAR just because it's an experiment I'm mostly involved in. There was an experiment called PAPER, which is led by the same people that did HERA. If you notice, they put the antennas on a very regular grid, and that will come back. Whereas here it's random. So this is one of the differences. What you get when you have things on the same, in a regular grid, you get the same baselines repeated many times, and you will see what baseline means in a second. So you'll have more signal to noise at one point in your data, but at one kind of wave number in your data, but it has other issues. So I'll come to the issues. What are the pros and cons? all what I wanted to say is that there are different, so this is MWA, which is in between, right? In between this is paper, this is HERA, which is the new, it's the American one, and this, actually it's the leading, in terms of sensitivity, it's the leading experiment so far. It's in between, so MWA is in Australia, it has its own history, I will not get you the history, but now it's in Australia, it has been always in Australia, but now it's led by Australians, it was led by Americans at some stage. It's in between our design of LOFAR and HERA, something in between. You see that there's regular things here, but they are also spread, whereas LOFAR is very random. So these are within mostly frequencies that go from redshift 6, more or less, to 11, something like that, okay? So that's the range we are looking at, which means frequencies in terms of frequency 180 megahertz down to 110, 115 megahertz. In Europe, it's a problem if you go below 115 because the FM radio, right? That's what you listen. The FM radio is below 115, so there is a wall there that you cannot. The only thing that you can pick up is below that, is below the FM band, which is about below 80 megahertz. So there's a blind, quite a big blind spot there. The future, of course, is SKA. SKA will have the low side of it. So SKA low has actually 2 experiments in it, because it's, well, it's one experiment, but it has 2 in principle. One is imaging, but then it wants to go really to very low frequencies, and very low frequencies is very difficult. Then you just only detect statistical things. I'll kind of expand on this. Recently, there was some spin-off LOFAR, which is called NINOFAR. It's in France, and what's the name? Saclay? No, not Saclay. Mononce. And it's a big station that is mostly focused on very low frequencies. So high redshift universe, about 2021. Redshift of 2021. So these are the current experiments, and you can see, I mean, the reason I put these, and there's LEDA, that's American one in California, in the Owens Valley in California. So they are, although they are all interferometers, but there's lots of leeway, and you will see in a few minutes where the leeway comes from. I mean, why the. Okay, so let's kind of go to the basics. I will not teach you radio astronomy, interferometry in details, but just to say. Normally, in interferometry, and in physics is a very important technique, interferometry, right? Fabry-Perot, I mean, whoever studied physics heard about interferometers. So you look at, in radio astronomy, you want to see a certain direction. So you have 2 antennas, and you correlate them. So there is a coherence between the 2 antennas. However, if you do it blindly, you get nonsense. So if I want to look at a certain direction in the sky. So it's an infinite source somewhere. So you have this plane wave coming, and it hits this with a certain angle, and it hits this telescope before this telescope. So if you want to correlate these two, you have to remember that the light you are, or the wave that you are correlating hits this before this in a tiny amount, right? But that's important. So when you correlate, you have to wait with this a little bit until this wave arrives here, and then correlate the two, right? So you register and correlate. So the most important piece, well, the most important, one of the very important pieces of technology in these things is the clock. The clock, you just have to time things very quickly. These are very short time intervals, right? So to get it right. So once you have this, this is called the baseline, and the wave is at this. If you decide the direction you want to look at, so it's b sine theta. So that's your baseline, right? And that's the interesting one. And if you work it through, you see that this is basically Fourier mode. It has to do with Fourier modes of the properties of your source, of the wave of your source. Which tells us already one thing that's complicated. If it's Fourier mode, it's dependent probably on lambda, on the wavelength. So for radio data, your response changes from and resolution and sky coverage and whatever, the beam, all depend on lambda, on the wavelength. Different wavelengths will fit differently in into the same, because you have a constant physical size. That doesn't happen, for instance, in a, well, it happens also in optical, but if you have a you know, kind of a dish or something, it goes to the center. The change in optical, because the wavelengths are so small, the changes are not that high. Here, it's serious. So every wavelength like this, every baseline, translates to a point in Fourier space, right? So because I take Fourier's analysis of this. I want to tell you one point before I move on. In radio, this is a classical wave. So we have a wavefront, we have polarizations, we can talk about these things. We have as much as you want in terms of photons. There is a famous, I think in Manchester, when they have this, there's this Jordan Bank. It has a, in Jordan Bank, they have these exhibitions to people normally. And one of the things that they put a small piece of paper. When you enter, you do this and pick it up. And written on it, you just have spent more energy than all the radio telescopes have absorbed in the last 100 years, right? Because it's so tiny, it's nothing. So you have so much of it. So, which makes it even more interesting, but also more complicated, because there are all kinds of things here. If you remember, VLT, for instance, wanted to do, the Very Large Telescope wanted to do interferometry, but that's in the optical. In the optical, it's much more difficult, because you are closer to the quantum limit. You have all kinds of issues. Here, that doesn't exist. Okay, so I'll go back to the same. So you have two antennas, and these antennas record. You know, you have some time span that you record a signal, and the signal basically translates into a point in this space, which is a weird space. It's Fourier space in 2 dimensions, V and U. I'm writing here between kind of parentheses kx, ky, or between. This is basically kx and ky. However, if I go to a different frequency, the same baseline will see this a little bit larger or a little bit smaller, depending on the frequency, right? So it depends on the frequency. So now let's focus on one frequency. So I'm looking at one frequency, and then each measurement have one point. But Earth rotates. As it rotates, it fills these things. So it depends on where your two baselines are. Are they, you know, east-west? Are they north-south? Or they are inclined, etc. They have different geometries here. This is the simplest and nicest geometry. So there's another thing. This is complex space, right? If you remember, but we are measuring real numbers. If you remember in Fourier space, for the condition for reality is that the conjoint, whatever it's called, I forgot the conjugate. Thank you, Andre. The conjugate is negative, is minus the. So basically, you observe half of it. The other half it comes automatically, right? And how long does it take to close? If you are in a good position, say it takes 12 hours to cover half the sky. That's it, right? I must say this is the nicest thing. Normally, you see things like this, and you know, so that's the. But this is just for educational purposes. And remember, you have different coverage at different frequencies. And the width here is important also. Now, why is it important? Again, let's focus on one frequency. How do I do imaging? In principle, if I have every point in Fourier space, here and here, so this is one baseline, that's that. Another baseline has different distances. It will cover a different thing at the same frequency. Another baseline has also a different one, will cover a different. In principle, you can cover the whole UV plane. So you have Fourier transform of your image of the sky. You can Fourier transform it back, and you get the sky, right? That's the idea. However, we wish we were so lucky, because you don't have a full coverage of UV space. And if you look at radio images done with an interferometer, they normally have these ghosts, these things like kind of. That's because you don't cover this very well, or not perfectly. So this is one of the issues they have to deal with. Now, there is another ramification of all of this. It's a weird space to measure. First of all, different frequencies, as I said, have different kx, ky, so you have to put them all in the same footing. The other dimension here is the frequency. So I told you the frequencies. So frequency in cosmology is redshift. Right? So you have this very strange space, kx, ky, and redshift. Redshift is real space, roughly. So you measure a mixture of real space and Fourier space. Okay? So that's a complication that you have to deal with. In principle, we can deal with that. And what you measure is called, what you measure is called visibility. And the visibility is kind of gets mixed. This is the coherence between these two antennas, and gets, because of the mixtures of all kinds of things, electronics, noise, Fourier transform, all of that, they are coupled to each other. The observed visibility coupled to the real coherence with this thing that is called Jones matrices. And it's a technical thing. I don't expect, plus noise. So this is your measurement, and this is what you need to go. I mentioned this. So this is, you start with the visibilities that I mentioned with your, what they normally also call it dirty image if you are talking in image plane. Dirty because it's not clean. You have to clean it with in terms of the contaminations. And yet from it, you can go to the image cube. That's what traditional radio astronomy did, with all of these rotation curves of galaxies. That they talk always about image cubes. Or you can go to Fourier representation. Okay? So in this field of 21 centimeter at high redshifts, the sensitivity is very low. You cannot do imaging. So our purpose is statistical detection of the signal, which is not nice, but this is how you start with these types of fields. So to remind you, you are very young. So I'll remind people like me that are, kind of old enough to remember. When the first galaxy survey came, CFA, all what people were hoping to have is excess variance, nothing else. A bit more noise than the noise you expect from the distribution of galaxies. And that's your signal. They are correlated then. This is what people measured. I'll remind you of another one, CMB. I'm old. When I was doing my PhD, I'm old. So when I was doing my PhD, 92, in the middle, COBE results came by. And then you ask, where are the images? How the sky looks like? Don't look at the images. It's just excess variance, excess noise that you expect. People got Nobel Prizes for this, right? Because it is really important. After a while, we waited for Boomerang and Maxima and all kinds of balloon bone and then WMAP and Planck to see images of the sky. So to say, okay, this is really a fluctuation there. It's reflected in the power spectrum. But our purpose in this field is measuring statistically, at least currently, statistically the signal. And statistically, to measure the signal, excess variance means power spectrum, right? So that's the name of the game. Yes, please, Christophe.
Yeah, it's probably very, very silly, but can you combine different senses, with LOFAR? Yeah, you will see now in a second why that's very difficult. We thought about, HERA is a bit, but MWA and LOFAR, we thought about this for a while. Even that is difficult. You will see in a second why. I kind of touched upon this in a second, but in principle, yes. In principle, yes, and I think Leon is writing some, and colleagues from Australia is writing some proposal on that along these lines. But it's difficult. So here is the kind of the answer. So this is the sensitivity to the visibility, how much uncertainty in your visibility, the thing that you measure. And it depends on the physical things. So this is the equation that we normally more or less take. So this is constants, KB is Boltzmann constant. This is something called the system temperature. And the system temperature has two components. One is the instruments. That's the noise of the instruments. And the other one is the sky. The sky produces noise. When you look at the sky, you see, I don't know, you will see it in a few slides. You see an image with a lot of points. And those are noise, right? At these frequencies, the dominant feature in most of the range of frequency is the sky noise, whereas in some part is the system noise. So this you have to understand very well. It's a bit technical, but this is something that we have to understand. So this is how well your antenna is, but even if it's perfect, you still have noise from the sky itself. right? Because the sky hides the signal. There's lots of things, point sources and things like that. Then this is the efficiency. That's also efficiency of your measurement. So how much so that's also the quality of your detector. dA is the area of the station of the interferometric element. The bigger it is, the more sensitive it is. The smaller it is, the less sensitive it is. And the square root of the bandwidth. Bandwidth means how much frequency you have, right? Frequency range. And the time, that's the normal thing with time. So it's the square root of the time. So the more you measure, the more you gain in terms of noise. The bigger the bandwidth, the frequency range that you integrate over, the less noise you have. The bigger the size of the antenna, you absorb more photons, etc. So it makes sense. What you have normally, money. And the money decides how many detectors you have, more or less, and how many connections you have between them. So you can decide, I can have a big detector or a small detector. And it makes a lot of difference. And that's part of the differences between the instruments. You can't, so this is kind of basically a certain area, a annulus that you have. So you can cover this with elements like this. Or you can take those and divide them to small things and cover it with this thing. And there's a big difference between the two. Why? This one has more sensitivity per element. But now ask how many pairs I can do. Remember, we have these pairs that we have to cross-correlate. Very little. This one has a smaller antenna, more noise, but have many more. And the question is, which one you go for? This, if you go to the extreme, gives you perfect sensitivity for power spectrum. This, if you go to the extreme, gives you perfect sensitivity for imaging, seeing the sky. And and both are important. Why both are important? Although we are after the power spectrum, but we need to see the foreground. What is disturbing our images, our data? If you don't know it, you cannot analyze, you can't say anything. So in all these experiments, there is a compromise between the two. So for instance, Hera went into the extreme. They said, okay, we just construct measurements, and then we have the closest things that we can, and as many as we can. Whereas the other extreme actually is LOFAR, because we have another, we are closer to this side. Yes, please, Christoph. You have 2 or 3, not many. Left-hand side, not many. So you need baselines, of course. So in this game, small is good in principle, but you have to take care of the foregrounds and the systematics. So if you are after power spectra and all what you have to deal with is noise, this is the strategy. But all what we have to deal with is not noise, it's systematics. That's the more difficult part. So it depends. So although all of us are interferometers in this game, but each one has different emphasis. Also, how you put the antennas. This is I'm describing an annulus here, but you can distribute them randomly versus on a grid like Hera, right? There's another thing. If you have these two things close, very close, you have the smaller the baseline, the bigger the scale that you probe on the sky. If you remember that. Just a second. So this has larger beam. This has a smaller beam. So these are things that you have to consider. And who's right, who's wrong? It's just a matter of intuition, how you build things, etc. Yes, please.
Can we have a combination of different antenna sizes, like ALMA, for example?
Yeah, ALMA is, well, the technology in ALMA is different. So one of the strengths of this, you can, in principle you can do these things, but you don't do dishes in this. These are not dishes, they are dipoles. Because if you do dishes, if you have many of those with dishes, that's incredibly expensive. You cannot do it. This is, that's the strength of this, okay? Okay, let me just, maybe the other side. Oh, God, what did I do? Right, and this is the power spectrum of the noise. It has basically, will not repeat everything, but it just has to do with all the things that's the beam, how many beams, how many cells, all of this noise, bandwidth.
and number of baselines and time. So this is what you get.
How do I know if I have a good image of the foreground? Why does that help me to remove the corresponding noise?
That's the next thing. Well, I can answer you immediately, but the foregrounds are, that's one of the main assumptions, are smooth in frequency, whereas the fluctuations are not smooth. There is another complication that comes in, which I will describe, but that's the main thing. So what normally I'm asked about, I mean, this is one of the main questions. How do you know you have foregrounds versus others? So what I normally answer to kind of give it to, in a simplistic way, it's like looking at a tree at the top of a mountain. A mountain is about 1,000 meters, right? And a tree is about 1-2 meters. A small tree, let's assume 3 meters, 4 meters, I don't know. And you normally can distinguish the tree from on the top of a mountain. Why? Because it has a different shape. So that's the main thing. I should say another thing about the foregrounds, but let me go ahead and try to say that later. So I covered this, I think. Right, and this is something that I always show. There are 3 steps in this. Detect the observations. It took us many years. So I started this just to, I'm kind of, again, I'm a theoretician by education. So I thought I'll do this for 5 years and move on with my life and do something else. That's our span of attention span, basically, is a few years. However, I've been in this business since 2004. So it's 21 years now, right? Because it turned out to be a much more difficult problem than we have, and we don't have a final result yet. We still have lots. We have learned a lot. So this is kind of something that I've never kind of thought I will be doing after 20 years. But but I must say it's such a rich problem and has so many aspects that I'm happy with that. So the first years we didn't have the detection, and the detection is, so this is a map of, this is CMB, this is a map of reionization. We focus on reionization here, but also cosmic dawn if you want. And then the light comes through the sky. There's lots of extragalactic sources that disturb us. There is the galaxy itself, which is huge. Suddenly you see this blue stuff. That's the galaxy in synchrotron. It's very prominent. So you saw in the previous thing when I talked about edges that the level of things is 1,000 kelvins, few hundred kelvins at least, right? 5,000 kelvins, etc. And the lower the frequency you go, the higher it is. It goes like the frequency roughly to the -3. So the lower the frequency, the more it explodes like crazy, the foregrounds. But this is the absolute value of the foregrounds. The fluctuations on the foregrounds on these types of things is much less. It's like the CMB. The CMB is 2.7 Kelvin. The fluctuations on it is 10 to the -5 Kelvin. So it's much smaller. And here we measure fluctuations. Why? This is something I forgot to mention. I'll go back if you allow me, because it's a very quick thing. You see this Fourier space? We never measure the central point. The kx equals 0, ky equals 0. That's the average. That's the mean. So we are always sensitive to fluctuations. And the fluctuations are much smaller than the fluctuations, than the 500. They are of the order of 1 Kelvin, 10 Kelvins, etc. Right? So that's the idea. So the data is there. This is LOFAR in one of its antennas. This is we used to use Blue Gene now, which cost us about 7-8 million euros. Now we use GPUs, which cost us 300,000 euros. So technology has moved a lot since we started. You see this range here. That's the ionosphere of Earth. Actually, this is the main problem. It's the ionosphere of Earth. Right. Okay. So go ahead. Right. So this is a real picture of a PhD, my former student, Vibor Jelic. He's now a full professor, so there's hope if you start with even in this field, there is hope for you to do stuff. So this is simulating the cosmological signal, the foregrounds. This is not a cartoon. These are real simulations. But his mother is an architect, so he has artistic flair to him, so he produced this, which is very nice. So this is what we see. We see the foregrounds, the signal, radio clusters, and galaxies. In our galaxy, we see all kinds of sources, free, supernova emergence, and synchrotron. Synchrotron is the biggest thing. And then all of this you see in your antenna. And the challenge is to peel out all of this and get this. That's the challenge. Of course, there are other things, the ionosphere, which is the nastiest thing, and you have the response of your telescope. And you have to deal with all of that. This is just a laundry list of all the problems we have. Just to give you an example, data, we have 3 to 4 petabytes of data. I repeat, 4 petabytes of data. If you understand what a petabyte, it's just, when we started thinking about this, we thought we will use €1 million just to store the data. Of course, Moore's law also saves us there. But there are all kinds of things. You have to fit all of these things, the foregrounds, I don't know, you have to calibrate well, etc. So what is the calibration problem? And I think this is the next. Before the calibration, we started looking at the sky, and we wanted to measure different. So I'm focusing now on LOFAR, but this is something similar to most, more or less, to most other experiments. We decided to look at the NCP, North Celestial Pole, because we can see it every night, although it's not the best one. And initially, we were very ambitious. We wanted 5 fields, but they told us, no, you will not have enough time. We focus on 3, 1, and 6. So I'll show you results from this and this with LOFAR, but also I'll show you results from other things. The most problematic objects on the sky that you have to fit very well is what in radio astronomy call them the A team. It's Cassiopeia A, Cygnus A, Taurus A. They are whopping in terms of radio. They are very, very strong. And that makes a difference. Why? Even if they are not in your field of view, if they are there, because you have this Fourier space, because we have these sharp things. If you remember, if you take a box and Fourier transform it as just a top hat, and Fourier transform it, you get this sinc function, which has infinite ringing. So something there might be picked up by the side lobes, what they call side lobes. This is the side lobes, it's this Fourier modes. So modeling these and taking care of them is essential. But not only these. There's lots of other things that you have to take care of. And so there's a sky that has a lot of structure, also in polarization. Synchrotron, our galaxy is very prominent in synchrotron in polarization, which is very damning. Yeah. We'll get to that a little bit more. So this is LOFAR. In a kind of, the center is here, but it's spread over all of Europe. It's a European experiment now. And now it's a small interlude with the funny kind of things. So this is when we started putting the antennas. This is the tractor that kind of flattened the fields. It looks like a simple tractor. This is a very, very high-tech piece of equipment. You need to, and I'm high, you need to get, listen to this, a football field, roughly, 100 meters by 100 meters, 2 football fields, flat to within RMS of 1 centimeter. In the field, right, outside. And there was a political push. The heads of Astron, who was kind of building this, wanted the antennas on the ground in 2008. But it was very, very muddy. It's just impossible to get RMS of 1 centimeter. It's just impossible. That's the tracks of the tractor. These are a couple of engineers. So, this is how it looked like. They flattened this area, but it's spread all over Europe, as you have seen. So the Netherlands is a swamp. So this tractor basically sunk into. We are still looking for the driver if you find him. So once they saw this, they said, "Okay, fine, we'll wait until the summer." And yeah, spring came, and then you have these fields that are very flat with this tractor, which has a lot of GPS and all of kinds of things, which is very high-tech. And LOFAR has 2 pieces of antennas. There is this piece, which is in the center, and this This is the low frequency, which is not interesting for our purposes. This is the high frequency, which are put, they look, they are basically just dipoles like this. And they are hidden just to protect them from the elements. This is the stuff that we are interested in.
Why can't you model this multiply?
You can a little bit, but not too much. Because, I mean, it's another, if you can't control it, because you need the angles to be completely correct between your elements. Right, because you form, you change the angle a little bit with the beam gets a bit ill-defined, and it's, until now, it's a problem. Yes?
I'll say this around seasons, because we get winter and spring.
Right, so you try to make it as stable as you can. It's quite stable. Once you put these things on the ground and you cover them, you can see here, you cover them with all kinds of, below them there is, so it becomes fine. As long as you don't, drive tractors around them, they are fine. And this is the way it looks now. It's very unimpressive. I was there. You look and you don't see anything because the grass has grown. So you have to look for them. But it's from above you see, it's very impressive. This is the very center, but we have a lot of them. And all of them look like these Mickey Mouse. You see these things here and here and here. Yeah. How much time do I have still? Not much, I guess.
Half an hour till coffee.
Okay, so 20 minutes. 20 minutes. Okay, so what is the purpose? The purpose is to see these fluctuations. This is the history. I showed you a couple of these things last time. These are the fluctuations in the neutral emission, and you want to see the power spectrum. That's basically the purpose. I always take this to honor my late colleague Khalid Bram, who started with me, and Leon Kopman started this project. He unfortunately passed away 5 years ago. In quite a sudden manner, but so this is I always mention just to keep his memory alive because he was really one of the pioneers of this. Okay, so I mentioned the foregrounds. Let me. This is I already mentioned. So the foregrounds have a number of components. I mentioned them. There's galactic foregrounds are the most dominant. There are something like 70%. There's synchrotron, diffuse, Bremsstrahlung, and individual supernova emergent, and there's extragalactic, which is about 30%. Now, these percentages have changed a little bit, but that's what we expected at the beginning. And this is a measurement that we did in 2009. This was the first measurement of this type. I think the battery is also. This was the first measurement of this type in 2009, where we measured the power spectrum of the foregrounds. And you can see how it's a power law, basically, right? Basically. Spatially, it's not as a function of frequency, but spatially, it's a power law. Now, where is the problem? I hope this explains the problem. In order to distinguish between the fluctuations that we want to measure and the other foregrounds, the Bremsstrahlung, the synchrotron, all of that stuff, all of these things are smooth as a function of frequency. Our signal is not, right? So in principle, you can do it easily. Where is the problem? If you have an antenna that has a polarized response, which means it's like a dipole, it responds in a polarized way. It picks up some of the polarization, and if you are not calibrating this antenna completely, part of your signal that you think is total intensity will be picked up from the polarization. And the polarization is nasty. Why? Because it has a structure in frequency, unlike the synchrotron in total intensity is very smooth. If you go to polarization, you see incredible structure. And without fixing this, you will have a leakage from your polarized part to your real part, your total intensity part. And then what you measure, you cannot claim I measured the EOR. You probably will measure polarization that leaked to your antenna, to your signal. So you have to calibrate your antennas incredibly well. And in the last 20 years, will be more, 21 years, I think 16 years of those are spent on calibration and are still spent on calibration. It is a very difficult problem. Now, how do you calibrate? So this is to show this. You have the signal, the EOR. If you have some stock skew that leaks, you can basically confuse both. So that's the purpose of this thing. So And why is that done? Why is that so complex? Because the ionosphere, our ionosphere, and that makes the calibration problem much more difficult. Our ionosphere changes all the time. So if you look at the same object from different sides of the ionosphere, you see completely different things, right? Because the ionosphere basically changes the refraction index, and you see different stuff. What is it similar to? Seeing in optical. What causes seeing in optical? Turbulence in the atmosphere, right? So how do you fix it? You look at guiding stars. And you say guiding stars should be point sources. Therefore, they should be just resolved as the PSF. You should see PSF there. But you don't see that. The atmosphere is scrambling completely. So you look at the guiding stars, you say, okay, they are scrambled in this way, I descramble them, and I descramble everything around them, right? That's how you correct it. This is similar to what we want to do. The problem is, we have no guiding stars, we don't know the sky in these frequencies. When we started, we had no clue what the sky looks like in these frequencies. It's a completely new window to the universe. In addition to the normal thing that you do in adaptive optics, which is the problem that you solve in optical, you have polarization here, which adds to the problem quite a bit. So you have to take but it's in principle, it's the same problem. Okay, so here is two nights. One very stable in terms of ionosphere. This is unstable in terms of ionosphere. This you throw away. You just can't deal with this. This is by its own is difficult. This makes it very difficult. Okay, so let me go down. Again, you have to remove the foregrounds. Yeah, I told you about the noise. You see these point sources? They are part of the noise of the sky. And you see these patterns. This is basically you haven't calibrated your Fourier space so well because that's a leftover. So you have that. You cannot allow any of this stuff because the signal is so small, any of this will kill it. So we started with this. You build a model for the sky, and you come up with very sophisticated technique. I had this student who was an applied mathematician that devised this method, how you slice the sky and take these as your guiding stars, not one point, but a region. It's a whole story, so which I will not add. Then after a lot of work, this is what you do with one night. This is I, Q, U, and V. So this is I. This is the total intensity. Before you fix anything, this is Q, U, and V. Q and U are linear polarizations. V is a circular polarization. You can see that there are very few things with circular polarization in the sky. And that's true. Circular polarization is very hard to create in the sky. There's a couple of stars that do that. Normally, you don't have them. And this is what we measure. We have to clean this, calibrate this. And this is our initial attempt where we started trusting the procedure of calibrating this. And so you calibrate this. There are some details about where it's this and what frequency, etc. And then you create this. This becomes your total intensity. And you can see round stuff. This is real sources. This is Q and U. They are related. They are linear. And nothing in the circular polarization. This is what we want, which is nice, but this level is not enough. We have to go much deeper. Okay, but that's the game. That's the game. You have to do it very well. Just a point here, because you don't have sources of circular polarization, you can use it to estimate your noise independently, right? So this is noise basically, and it tells you about your sensitivity and all of that stuff. Okay, so. This is a very deep image of the North Celestial Pole. Again, this is a real image. We have published it in a very kind of, this took us a lot of effort. But you see all of this, you take out. Now, in optical, what do? You throw away the region with the source, right? That's what six tractor is and all these methods. If we do that here, we are left with no sky, nothing. So what you need is to fit out. And that's a much more difficult thing. It's not to ignore, but to fit out and trust your procedure so that you can get something serious in this. So this is just to show you finally, after you do this, so this is your You decompose the sky to these limits, so this is a simulation that was done by Florent Mertens from Paris Observatory. You look at the extragalactic sources. The way you should see them, they will be sources. This is the frequency, so they will have a straight lines. It's the same, power law as a function of frequency. Galactic emission, they are diffuse. They will be longer, but they're like this. Where the complexity comes from the instrument. You remember the instrument I told you? Different frequencies has different sizes, right? Different responses. Which means what you get is, as a function of frequency is not this. You get this. Right? Because the frequency, the sensitivity and what you measure changes as a function of frequency. So it should look like this, basically. Like this. So and this is exactly what you see here. And so there is a way in this method to describe this. It's called the UR window or the wedge. So this is a k parallel, k perpendicular dissection of your Fourier space. K perpendicular goes along the sky, across the sky. K parallel goes deep. So that's the redshift. So that's the frequency direction, right? Without the instrument, you would expect the intrinsic foreground to sit in, because they are very smooth, K parallel will be very low. So they will sit here, and your signal will sit here. But because your thing is not, it responds differently to different frequencies, it has this structure. It's called the horizon. And the foregrounds are sitting here. So great. If you have this understanding, you look here. That's your EOR window. You have the signal. You just pick it up, and we go home. I wish that was the case, because there's lots of leakage from this side to this side. Actually, people who started this, looking at this in this way, simplistic way, retracted all of their papers of publications. That's the paper project and other projects. We have never done that because our approach was very, very different. So this is good for understanding. It's not good for enough to do the real thing. To do the real thing, you have to do this foreground extraction, not avoidance. I'll skip all of that. So recently we published this. This is our best result so far. This is 3 redshifts of the North Celestial Pole, the NCP. And we measured the power spectrum. So this is the spherically average power spectrum. This is what I mean by delta. It's not the real power spectrum. It's multiplied by k cubed. And it's not dimensionless. It has a dimension of temperature. If you do this in fluctuations, density fluctuations, they are without dimensions. In this case, they have dimensions because you start with dimensions. And this is our measurement. This is much better than what we had before. Before we had this measurement in 2020, which we published. This is 140 hours of data at redshift 9. We didn't have that at redshift 10 and 8. 2017, we had data from one night that we have. So there's a lot of progress. This is the thermal noise. You want this to reach here. You want your error to be smaller than the thermal noise so that you can say if I detected something or not. We are getting there. Now, this is 140 hours. This is not perfect. We still have a lot to do in this, but we have 1,500 hours in this field. So we have lots of data still that and I think we are, if we do a good job, we can get there. So this is a summary of the status of the field in 2017. 2017 was very little. What you see here is delta squared. That's the power spectrum with the k cubed component. And it has these dimensions. As a function of redshift, at a k of roughly 0.1. Right? So a certain wave number, and you look at how things stack up. And you can see the best was Beardsley, 2016, Patil, that was my student. We were LOFAR. These are LOFAR. And this is Bachiga. That's the GMRT result. And this is also from MWA. So they published 2 papers at that year. This is the status in 2019. You could see that things are going in low. These are the expectations from models, okay? And now we expanded the window. There is NINOFAR here. There is SKA, which is here. These are the noise of SKA. This is the noise of LOFAR, right? So if you go sensitivity below this, you can detect stuff. So this is what we expect after 1,000 hours of LOFAR. This is from 100 hours of SKA or 1,000 hours of SKA, right? So there's a future to this, provided you get the systematics of, and this is the current status. Look how much progress we have here. This is remarkable. Still not there. This is delta squared. So if you take the square root of this, it's about 30 millikelvin. The signal is of the order of 10 millikelvin. We are getting close. The best result, just a second, the best result comes from Hera, which I showed before. I didn't talk a lot about, but it's the same types of struggles they have. And Mertens 2025. Yeah, maybe. I think this is the stuff that we have published recently. It's this. We also have from NINOFAR, which is the French side, recent result, which is this. This is what you expect from edges, right? If edges was correct. So we are getting close to ruling out also the edges result. All kinds of experiments. Yes, before I continue. Yes.
I don't understand why there is only 100 of hours because.
You mean why do we analyze only 100? Okay, so here's the game. You have a method for calibration. You want to calibrate, you take data and calibrate it. So the data to calibrate 10 hours, one night. We normally observe NCP, especially in the winter. So the nights are long, so 12 hours, 14 hours. You take that night and calibrate it with the method that you have. And that takes 3 months, right? Because I will not get into it. It's so demanding. It's just because it's a lot of data. And then after 3 months, you look at it, you say, oh, this is not right. I have to improve something. Then you go think for another month or 2 till you find what it is. And then you improve your thing, and you go do it again. And then another 3 or 4 months, and you have another result. It's fine, but yeah, there's another systematic. That's the game. A year passed, and you haven't published anything. So we have been learning a lot. So the way we did it, if you look at the data we had, Patil et al. Had what night? 8 hours or 10 hours. Then we went down to 100 hours, 1 frequency, and then we did in 3 frequencies. So an order of magnitude. The next one is another order of magnitude. But you have to do it this way, because every time you go deeper, you discover new systematics. That's the word of systematic. It's not statistical. It's systematics. Okay, 5. Okay. These are models from signals that you expect from models, or different models. This is the sensitivity of different things, and this is the models. So you run a couple of different models with different parameters, and this is the range you get. So you might get lucky and detect things with LOFAR. You might not get lucky, and you have to wait for SKA, right? So that's or Hera. Okay. Now, I told you we had 2 windows. The other window was this 3C196, which is a 3C source. 3C source is the Cambridge catalog of the third Cambridge catalog has sources of radio, and then you look around. There's why we chose this. There's a whole story, kind of that has to do with astronomical aspects. But we chose that field. It doesn't appear every night. However, the sensitivity per observation to that field is better than the NCP. But for a long time, we didn't know how to calibrate it. However, with what we learned from the NCP, after all of this effort that I mentioned, we started understanding how we calibrate a field like this. And then suddenly we succeeded. And this is 6 hours of data on the NCP. You can see here that these are the things that we started with, and you get immediately with 6 hours 54 millikelvin sensitivity, which is impressive. It's just unbelievable. I didn't believe it when I saw it. So this is very new. We just published this. So we have another 1,200 hours on this field. So things are rapidly moving at this stage, and they are not as grim as 20 years ago. So this is and the thing is that with these points, we are already below the noise, right? I should mention that we are not interested in the noise. We are interested in the variance of the variance, the noise over the noise, because that's the uncertainty on the noise. You have to, but that's a detail. Anyway, but we are getting there. It's very impressive, actually. Next steps, we analyze more data, et cetera. Sky models, improve our calibration. The others are doing something similar, et cetera. So now to the analysis, which the last few minutes. A couple of minutes. What does the analysis give you? You start with this. You have models. These are models of power spectra as a function of K of many models. And these are your measurements at a certain K. These are ruled out. You throw them away. So this is how you do. So all the time now, we have upper limits. And the upper limits allow us to rule out certain models. Hera, because it's the best, have already ruled out almost completely the possibility of cold IJM until redshift 6, which is remarkable. Because if you remember, cold IJM means there's more fluctuations, right? So in LOFAR, we did some experiment here, which is, don't trust this, but we published it, but it's just as a method. We went to the drawing boards and used AI to start understanding the difference between foregrounds and non-foregrounds and sky and non-sky, etc., stuff like this. We managed to reduce this data to here. Oh, I saw this. Oh, right. This is wonderful. Yeah, we still, it's very promising initially. The problem is that once you do these exercises, all the bins become cross-correlated. So you have to understand that. But you reduce this to this, we are in business. We are very close. This is 100 hours, even 10 hours. I can't remember. No, this is 140 hours. So we are really in business here, if we manage to do it, to convince ourselves that this is the right method. The best result, so I wanted to talk about how we estimate the parameters. I have no time, so I'll stop here. I'll keep it in the thing that I will. So let me finish this. As you can see, I've prepared more than I can explain. I talk too much apparently in these types of things, but it's fine as long as you understand what I explained. I want to end up with this. I love this. This is from the book, the Book of the Dead in the End of Darkness. It says. So this is the title of this from the old Egyptian, so I think it's Osiris says, "I am the only being in the abyss of darkness. From an abyss of darkness came I forth, ere my birth, from the silence of," and it continues. And this is let the mystical circumambulation take place onto the path of darkness that leadeth unto light, with the lamp of the hidden knowledge to guide the way. It's wonderful. This is written 3,500 years ago, 400. This is, He's talking about the Dark Ages. Wonderful. I'll stop here. Thank you very much for listening.
Great. Thank you so much. Questions before coffee?
Has adaptive optics not been tried to solve the problem of fluctuating ionosphere?
No, but this is, well, I mean, effectively you are doing like adaptive optics, but this is not optics. It is not optical. It's radio. And the issues are very different. I mean, they are, I mean, heuristically speaking, just kind of broad brush, they are similar. But again, you have different issues because, first of all, you have a wave front, you have these polarizations, and you have these leakages. So you have to understand not only the total intensity, what you measure normally in telescopes, but also the polarization aspects. And that is, and why the polarization is very difficult, because you have the ionosphere, it's magnetic. And it has these, and it's ionized. And so it mixes things together. And you don't have that in optical at all. All what you have in optical is turbulence, basically. That's it. Here, it's much more difficult. It's a more dimensional aspects go into it, so that's why it's so difficult. But the technique is roughly, at least broad brush, is kind of the same type of thinking. Yes, please.
This might be a simple question, but how do you know or decide which part of the sky you're looking at?
Right.
How do you aim the
Right. That's a very good question, and it took us a long time to do, but there is a clear answer in the image. So there's an image that I showed before. We're getting close. Yeah, here it is. What you see here in the background, not the areas, is the Haslam map. The Haslam map was done on 408 megahertz. So this, is, again, is related to history. Radio astronomy, if you look at what Jansky saw very, very, tens of megahertz. That's the first observation. And he managed to say that it's the galaxy. He managed to time it with the galaxy, etc. But once the 21 centimeter line was discovered, radio astronomy moved to higher frequencies, to 1.4 gigahertz. And people didn't go back to low frequencies for a long, long, long time. The reason being is these foregrounds, they go like the frequency to the -3, roughly 2.7. So, you go you go a factor of 2 in frequency down, larger wavelengths, you go a factor of 10, roughly, in terms of difficulty. Without talking about the ionosphere or anything, just the foregrounds become much more formidable. So our guidance for choosing the fields was this. So this is the only map that has this 400 megahertz. It's not low frequency enough, but this is what we had at the time. So it's a very famous map. And you can see that how things look in these frequencies. If you look at the CMB, so that's microwave, that's much more, right? That's hundreds of gigahertz. If you look at the galaxy, it's limited to the center and at these low frequencies, you see these flares of stuff that you see all the time. It's just completely different thing. This is a supernova remnant, apparently, or in our galaxy. And so it looks very different. So in this frequency range, which is not exactly what we want, but it's the closest we could get, we wanted the quietest regions. And there was a question, do you want a prominent radio source inside? That's NCP. There's no prominent radio source inside. Or you want a prominent radio source inside. That's the 3C196. And we didn't know the answer for a long time. It seems like this is the better way. But yeah, it's a kind of astronomical, interesting issue. Okay?
Yeah, but can I follow up? So how do you actually point at a given cloud?
Right. So it's the timing. You say that direction will create a difference of so and so picoseconds, right? And so that's how so it's the timing that decides which right. And there is a shadow of that side into this. So you always have these. So you have to get rid of it. But that's part of the deal. Yeah, it's time. It's because you just have a dipole. It's like this, nothing else.
So you mentioned multiple times that you assume that the foreground is kind of smooth in the frequency.
Yeah.
So how good is that assumption?
So far, so good. In total intensity, in polarization, I can show you actually. So this is part of the PhD. I mean, this is a part of the hidden, part of the hidden things that I have here. You see, and then we do here. Yeah. So this is how it looks like in polarization. It's crazy. This is an integration over a number of frequencies. This is I think it's the NCP, yeah, in polarization. Look at these canals. They are called depolarization canals. They are thin. What the hell are those? This is a completely different work, but you can learn. I mean, if you are interested in the polarization, that's a whole field. It's a huge field. So Weber, who was my student, basically moved completely to that direction. You look at the structure, and this is 10 degrees or more, roughly 10 degrees or 8 degrees. That's huge on the sky. It must be very close. So we think this is where the solar environment meets the ISM. so it's basically different physics. And you see this also in Planck. You see this is the colored stuff we did ourselves.
And you can cross-correlate it with Planck. You can see different polarizations. You see different colors, so that's that structure. And then you go to the last one. You see this structure here that we see in our data. This is in Planck, right? Because Planck had these orientations of magnetic field. So this is real stuff. Yeah. We don't understand it, but it's real.
Any last questions?
Yeah.
Did you mention the frequency is the redshift? Is it right? The frequency is redshift?
Yeah, I mean, it's related directly to redshift. Right, it's delta lambda over lambda. So you know lambda. So delta lambda is the difference between, lambda is 1,420, not lambda, 21 centimeter, right? So delta lambda is whatever lambda you measure minus 21 centimeter or 21 centimeter. And that's your redshift, 1 plus z, right? That's the definition of redshift.
So, may I cross promote?
Yeah, absolutely.
If we want to detect the signal from the dark ages,
Yeah.
that means does it mean the frequency is much more lower?
Yeah, 10, 20, 30 megahertz.
I think that is the reason why we
Go to the moon.
Go to the moon.
Right, that's what I mentioned yesterday, absolutely. That's the next exciting thing. And in my summary, I say that one of the next exciting things is the moon. Right, lunar observatories.
Is it because the radio pollution is very
No, because I mentioned that the foreground is still very prominent, but the problem, but on Earth, because the ionosphere dances all the time, changes, right? The sun basically heats it up, and magnetic field change, etc. The scrambling is very serious. You go to the dark side of the moon. Okay, yeah, there's a formidable foregrounds, but they are much simpler to model, in principle at least. Of course, there are other issues there.
Okay, so I think we should go to coffee, but let's thanks to you.
Yeah, thank you very much. Thank you.